So thank you so much to the organizers for the invitation. My talk is going to be based on joint work with several people, including Stephen Karp, Lukowski, Parisi, Sherman-Bennett. So let me give a little overview of my talk. I will start by explaining what is the positive Grassmannian, and then I'll introduce the main object, which is the amplituhedron. And I'll explain how we can study it from several points of view, including matroids, tilings, triangulations, cluster algebras, and along the way we'll see some connections to nice objects from combinatorics, including Eulerian numbers and the hypersimplex. And I guess one thing that you'll see as I give my talk is that we understand a lot of things about the amplituhedron when the parameters k and m are small, but many questions are still open. Okay, so let me start by reviewing the Grassmannian. So the Grassmannian, GKN, is the set of all k-dimensional subspaces of an n-dimensional vector space. And we can represent elements of it by full rank k by n matrices. So here is a full rank 2 by 4 matrix, and we will identify such a matrix with the row span of this matrix. So that gives us a 2-plane. And I'll be talking about Plücker coordinates. So if I is a k-element subset of the numbers 1 through n, then the Plücker coordinate p sub I of c is the minor of the k by k submatrix of C located in the column set I. So if this is my matrix C, and if I is 1, 3, then P 1, 3 of C is the determinant of this submatrix, which gives me 2. Okay. And now we can associate what's called a matroid to any such element of the Grassmannian. And the matroid of C is just the collection of k-element subsets of 1 through n where the Plücker coordinate is non-zero. So it's just recording for me which columns of my matrix are independent or form a basis. Okay, so work of Gelfand, Goreski, McPherson, and Serganova introduced the matroid stratification of the Grassmannian. And so it's a way of partitioning the Grassmannian into pieces. So if script m is a collection of k-element subsets of 1 through n, then we let Sm be the subset of the Grassmannian where your Plücker coordinate p sub I is non-zero if and only if I belongs to that collection. And sometimes these pieces are empty, but if they're non-empty, then we call them matroid strata. And so this gives us a way to decompose the matroid into pieces. Decompose the Grassmannian into pieces. Okay, so now I'll let E1 through En be the standard basis of Rn. And so Ei is, you can think of as a 0, 1 vector with a 1 in the ith position. And then if I is a subset of the numbers 1 through n, E sub I will be the sum of the little ei's. So it's the 0, 1 vector with 1 precisely in positions given by capital I. And now we have a moment map from the Grassmannian to Rn defined as follows. So C here is our element of the Grassmannian, so it's a k by n matrix, if you like. And we map we map C to a point in Rn. And this is really just think of it as a linear combination of the ei's. They're weighted by Plücker coordinates. And in the denominator, I'm summing by the squares of the Plücker coordinates, just so that the sum of my coordinates of all points adds up to 1. Will add up to k, actually. Okay, so remember our matroid associated to a Grassmannian element was just the k-element subsets where the Plücker coordinates are non-zero. And now there's 2 ways that we can associate objects to this matroid. One is the matroid stratum that I told you about, the collection of elements in the Grassmannian, where Plücker coordinates are non-vanishing if and only if I belongs to the collection. And the other is a polytope, the matroid polytope, and this is defined to be the convex hull of the E sub i's where I belongs to M. Okay, so two different geometric objects, but they're related. So Gelfand, Goreski, McPherson, and Sarganova showed that the moment map image of a matroid stratum is exactly the corresponding matroid polytope. So these two objects are related via the moment map. Okay. So, so as a very simple example, if my matroid M is all k element subsets of 1 through n, then this corresponds to the matroid stratum where none of your Plücker coordinates vanish. And the previous theorem implies that the moment map image of this stratum is the whole matroid polytope, namely the convex hull of all E sub i's, where I is a k element subset of 1 through n. And so this polytope is called the hypersimplex, and I've drawn it here for delta. This is delta 2, 4. So this little octahedron over here is the convex hull of all E sub i's, where I is a 2-element subset of 1 through 4. Okay, so there's many beautiful properties of matroid polytopes. For example, there's this beautiful characterization that a matroid polytope is precisely a 0-1 polytope such that every edge is parallel to EI minus EJ for some I not equal to J. Okay, but there's also some very bad things about matroid strata. The topology is very bad. Minyoff's universality theorem says that the topology of a matroid stratum can be as complicated as that of any algebraic variety. Okay. So, so now I want to kind of revisit the previous picture where we add in the adjective positive. And so I'll tell you about the positive Grassmannian, which goes back to work of Lustig, Reach, and Postnikov. So we'll define the totally non-negative or the positive Grassmannian to be the subset of the real Grassmannian where all of our Plücker coordinates are non-negative. And inspired by the matroid stratification, you can partition this positive Grassmannian into pieces based on which Plücker coordinates are strictly positive and which are 0. So again, if M is a collection of k element subsets of 1 through n, we can let Sm, T, and n be the set of all elements in the positive Grassmannian where the Plücker coordinate p sub I is strictly positive if and only if I belongs to the collection. Okay, and then of course the other Plücker coordinates must be 0. And in contrast to the terrible topology of the matroid strata, Postnikov showed that that these pieces now are actually cells. So if SMTNN is non-empty, it's actually a cell, in other words, homeomorphic to an open ball. And so this gives us a cell decomposition of the positive Grassmannian into pieces called positroid cells. Okay. Okay, so this is just a review of the notion of matroid, the matroid associated to a Grassmannian element, and then the matroid polytope being the corresponding convex hull of EIs. And when I start from a matrix C in the positive Grassmannian, we'll call M of C a positroid, and we'll call the matroid polytope, gamma sub M, a positroid polytope. Okay, so, so in Postnikov's 2006 preprint, he classified all of the cells of the positive Grassmannian and showed that they are in bijection with several combinatorial objects. One of them is equivalence classes of some kind of planar bicolored graphs. And so this is a picture of a planar bicolored or Plabic graph. That's the first set of objects. And the second set of objects is some kind of permutations. So decorated permutations on n letters with k anti-exceedances. And I'll just show you, I don't want to kind of give all details, but I'll just show you how we can go from such a graph to a permutation. So my graph has 9 boundary labels. And so I'm going to write down a permutation on 9 letters. And we're going to basically take walks on the graph, starting from boundary vertices. And whenever we see a black vertex, we'll go right. And whenever we see a white vertex, we'll go left. And so, for example, if we start at 1, we'll go here, see a black vertex, turn right. Go here, see a white vertex, turn left. Now we see a black vertex, so we'll turn right. Now we see a white, so we turn left, and we end up at 8. So 1 goes to 8. I'll do one more example. If we start at 2, we see a black, turn right, see a white, turn left, see a black, turn right, see a white, turn left, see a black, turn right, see a white, turn left, and then we end up at 5. Okay, so this is, so I haven't said yet how positroid cells are in bijection with either of these objects, but I've just explained a kind of a link between Playbig graphs and some kind of permutations. Okay, and so when a cell is labeled by a permutation pi, then we'll just refer to the corresponding cell as S sub pi. Okay. Okay, but now I want to explain how you get a cell from a Playbig graph. So remember, these Playbig graphs are some kind of planar bicolored graphs. They're embedded in a disk. They have boundary vertices 1 through n, and they have internal vertices black or white. Okay, and we can assume our graph is bipartite and that every boundary vertex is incident to a white vertex. Okay, and so if we have done that, then I'll now show you how to get a matroid from such a graph. And it uses matchings, uses perfect matchings. So, so I will associate a collection of k-element subsets of 1 through n to a graph as follows. I'm going to look at almost perfect matchings of G. So what is an almost perfect matching of G? It's going to be a subset of edges such that every interior vertex touches exactly one of my edges. Okay, so these are the almost perfect matchings of my graph G. And you can see that every interior black or white vertex is touching precisely one edge. That my chosen edges are those shown in orange. And now from these almost perfect matchings, I'm going to record which boundary vertices are touched. So for example, in this graph here, my orange edges touch 1 and 2. Here, the orange edges touch 1 and 3. Here they touch 1 and 4. Here they touch 2 and 3. And here they touch 2 and 4. And so in this example, M of G is 1, 2, 1, 3, 1, 4, 2, 3, and 2, 4. And that's my matroid that I will associate to my graph. Okay. And then the theorem is that this M of G is the set of non-zero Plücker coordinates of some positroid cell, and all cells are obtained like this. Okay. Please stop me if you have any questions. Okay. So now I want to explain what is the amplituhedron. So this object was introduced by physicists Nima Arkani-Hamed and Yaroslav Trnka in 2013. And before I actually tell you what it is, I'll just say the amplituhedron is the image of the positive Grassmannian under a simple map. Okay, so now let me tell you what is that map. And it is really simple. So an amplituhedron is indexed by 3 positive numbers n, k, and m, where k plus m is at most n. And it's also defined using a fixed choice of matrix Z. So Z is going to be an n by k plus m matrix, where the maximal minors, or the Plücker coordinates, are strictly positive. And now I'm going to use Z to define a map. And this map is a map from the positive Grassmannian of k-planes in n space to the Grassmannian of k-planes in k plus m space. And it's really simple. I just start from my k by n matrix C, representing a point in the positive Grassmannian, and I just do matrix multiplication. I map C to CZ. It's a lemma that CZ is full rank, and so it represents a point in the Grassmannian of k-planes in k plus m space. So that's my map Z tilde. And then the amplituhedron is simply the image of the positive Grassmannian under this map. Okay, and by definition, this is a subset of the Grassmannian of k-planes in k plus m space. Okay, so a few comments that I'll make. One is that the amplituhedron depends on Z, but many of its properties appear not to. It has full dimension km inside the Grassmannian, so it has the same dimension as the Grassmannian that is living inside. When m is 4, which is the case most interesting to physicists, its volume is supposed to compute scattering amplitudes in n equals 4 super Yang mills. And why is that? That is because this BCFW recurrence, so Brito, Cachazo, Fang, and Witten, this recurrence for scattering amplitudes can be reformulated as giving a kind of a triangulation of the m equals 4 amplituhedron. Okay. Any questions on the definition?
So this amplituhedron is not inside Euclidean space.
That's right, that's right. It's living inside the Grassmannian, yeah. And it's not, yeah, despite the name, it's not a polytope. Yeah. Okay. So I'll just say there's some simple special cases. So first, if m equals n minus k, then our matrix Z will be a square matrix with maximal minors positive, and then Z tilde will be an isomorphism. So in this case, the amplituhedron is really just the same as the positive Grassmannian. Okay, now let's talk about a more interesting special case. And so that's when k equals 1. Then our amplituhedron lies inside the Grassmannian of k-planes and k plus m space, which is one plane and 1 plus m space, which is projective space. And the easy claim is that this is equivalent to a cyclic polytope with n vertices. Okay, so why is that true? Let's just look at a small example. So let's take the case where m is 2. And so then my matrix Z is a n by k plus m matrix. So it's an n by 3 matrix. And let's let Z1 through Zn be the rows of Z. So this is, so here's my Z matrix. It's an n by 3 matrix. And the fact that its maximal minors are positive will imply, if you think about it, that if I draw each Zi in P2, then they're in kind of convex position. So if I draw them in P2, the Zi's will have this order, will be ordered like a polytope. And now how do we think about the amplituhedron map? So Z tilde is the map from the Grassmannian of 1 planes in n space to the Grassmannian of k planes in 1 plus m space. And what we're doing is we're just taking a 1 by n matrix and we're just multiplying it by the z sub i's, and so it's c z. And if you think about what matrix multiplication does, well, if one of my C matrices is just EI, the 0, 1 vector with 1 in the ith position, EI will just go to my row vector ZI of Z. And so I will have all of these points in the image of my map. And then if I take now, instead of E sub I, I take a positive tuple of numbers, C1 through Cn, then I'm going to be sweeping out this whole polytope. Okay, so that's why when M is 2, the amplituhedron will just be a polygon. And for K is 1 and higher M, we'll get a cyclic polytope. Okay. Okay, so we again get this nice special case when K is 1. If you look, on the other hand, at M equals 1, it turns out that the amplituhedron recovers the bounded complex of a cyclic hyperplane arrangement. And this is some pictures of what your amplituhedron looks like when M is equal to 1. So it's not convex, it's not, yeah, but it's not convex, it's not a polytope, but it's still very combinatorial.
The triangulation.
Sorry?
So does the pictures remind triangulations?
Oh, yes, yeah. So this is, so I've just shown how, so I've shown the hyperplanes of the arrangement, and yeah, so basically there's a very nice hyperplane arrangement called the cyclic arrangement. It's chopping space into these different regions. Some are bounded, some are unbounded. And the amplituhedron gets identified with the bounded complex of the arrangement. So the union of all of the finite regions.
This is facet of triangulation. So picture of facet of triangulation.
Oh no, these are actually pictures of amplituhedra. Yes, so yeah. Was there another question?
Yes, what is the dimension then?
So, A, N, K, M always has dimension K times M. And yeah, so the dimension will be the product of these two numbers. Yeah. Okay. So now let me say a few words about oriented matroids, or rather how these things are connected to matroids. And so up here I just have a reminder of the definition of amplituhedron. So this amplituhedron is the image of the positive Grassmannian under a map, and it lies inside a Grassmannian. And we'd like to have some good coordinates with which to talk about it. And we want coordinates that lie directly inside of, describing it directly inside the Grassmannian of K-planes and K plus M space. Okay, so now I'm going to describe what are these coordinates. So let's let Z1 through Zn be the rows of our matrix Z. And let's let Y be an element of the Grassmannian of K-planes and K plus M space. And I'm viewing it as a K by K plus M matrix. And let's let I be an M element subset of the numbers 1 through N. And now I'm defining a coordinate. This coordinate is, so this Y I'm thinking of as possibly an element of an amplituhedron, but it doesn't need to be. And then I define the coordinate YZI as follows. So I take my matrix Y, so that's here. This is a K by K plus M matrix. That's this top part. And then underneath it, I put M rows of Z, precisely the rows of Z corresponding to my chosen subset. Okay, and each row of Z is a vector of length K plus M. And so I'm basically filling this out to be a k plus m by k plus m matrix, and so we can take the determinant. And that's the coordinate. That's the coordinate that we're using. So this is called a twistor coordinate, and they first came up in this paper of Arkani-Hamed, Hamed and Trnka. And these are coordinates, elements of this Grassmannian k plus and k plus m space are determined by the twistor coordinates. So you can actually describe the amplituhedron using these coordinates. Okay. And now, inspired by the matroid stratification of the Grassmannian, we can define the amplituhedron sign stratification, where we decompose the amplituhedron into pieces based on the signs of these twistor coordinates. And then we'll call the top dimensional pieces chambers. Okay. So this is just a review of our notion of twistor coordinate. Okay. And so how many coordinates do I have? Well, I have as many coordinates as there are m element subsets of 1 through n. And so now given sigma, a sign vector of length n choose m, we define the amplituhedron chamber. Oh, that's weird. Sorry, I'm having a technical issue where I can't go down anymore. It's very strange. Okay, that's not ideal, but I can use the page down button. So the amplituhedron chamber is the subset of elements in the amplituhedron where the twistor coordinates have prescribed signs based on this vector of signs sigma. And it's, in general, it's open which chambers are realizable. In other words, not always empty. However, we know everything when m is 2, also when m is 1. And okay, so I'll tell you what that is because it has a nice connection to combinatorics. So, so this is our definition of amplituhedron chamber. And we'll say that a sign vector sigma is realizable if there's a z such that the corresponding sign chamber is non-empty. Oh, now it works again. Okay. And so it's sort of a surprise, but when m is 2, the realizable amplituhedron chambers of the amplituhedron are precisely counted by the Eulerian numbers. So they're precisely counted by permutations with a fixed number of descents. And so the Eulerian numbers have many combinatorial interpretations, but one significant fact is that the volume of the hypersimplex is that same Eulerian number. And this is a shadow of a kind of a strange duality between the amplituhedron when m equals 2 and the hypersimplex. Any questions?
So what the counter?
Yes, so I will say, yes, I'll say the duality. Okay, but in order to explain the duality, I need to talk about tilings and triangulations. Okay, so this is just review of the notion of tiling, of amplituhedron. And so remember, the amplituhedron is the image of the positive Grassmannian under a map Z tilde. And this map is surjective, but in general it's not injective. And since it fails to be injective, one would like to find, it fails to be injective, and moreover, this object has dimension k times m. And so we'd like to find a km dimensional cross-section of the domain which Z tilde maps injectively onto the amplituhedron. Okay, because we'd like to express it as the image of something that maps injectively onto it. Okay. All right. Now we have this cell decomposition of the positive Grassmannian, and we have this map Z tilde, which is a continuous surjective map onto the amplituhedron. So now we'll define a Z-induced tiling of the amplituhedron to be a collection of closures of images of km dimensional cells S pi such that the map Z tilde is injective on each cell. The union of these objects equals the whole amplituhedron. And the interiors of those objects are pairwise disjoint. So this is kind of the natural way you might try to generalize the notion of triangulation of polytope, perhaps. Okay. So once we have that notion, we can look at what we get in special cases. And we can look at how big are the tilings, like how many pieces are in a tiling. And so you get a lot of interesting combinatorial numbers when you do that. So for example, when m is 1 or m is 2, you get some binomial coefficients. So that's the number of tiles in a tiling. When k is 1 and m is even, you get a different binomial coefficient. And when m is 4, you get these Narayana numbers. Okay, so these sizes of these tilings are very interesting combinatorially. And then you can say, well, can I generalize the numbers here? And I'll tell you what's the natural generalization of those numbers. So let's let m of ABC be this number. This number happens to be the number of plane partitions contained in an A by B by C box. And then the statement, which is true in all the previous examples, which is that the cardinality of a tiling of the amplituhedron for even m is exactly the number of plane partitions contained in a k by n minus k minus m by m over 2 box. Okay, so that's consistent with all of the known results. And it also suggests some intriguing symmetries on the level of the amplituhedron as well. Okay. Okay. Any questions before I go on?
So, is there any good reason of why plane partition should come into?
I'm not sure if there's a good reason, but for m is 1 and m is 2 and m is 4, we can give a bijection between pieces of a tiling and either a single lattice path or 2 lattice paths inside a rectangle, which are in bijection with plane partitions. Okay. Okay, so now I can say something about tilings of the amplituhedron when m equals 2. So in this case, we understand everything. So recall that the hypersimplex, delta k plus 1 comma n, is an n minus 1 dimensional polytope in Rn. And remember, it's just the convex hull of all of the EIs, where I is a k plus 1 element subset of 1 through n. Okay. Now, on the other hand, the amplituhedron is some kind of non-polytopal km dimensional subset of the Grassmannian. Okay. But what was very surprising when we first realized this was that the tilings of the m equals 2 amplituhedron and some kind of subdivisions of the hypersimplex are very closely related. I mean, are in bijection. So, okay, so this is just a review of the notion of tiling of the amplituhedron. It's this collection of closures, and I'm specializing to the case m equals 2. So it's a collection of closures of images of 2 k-dimensional cells, where z tilde is injective on each cell. The union of these pieces is the whole amplituhedron, and their interiors are pairwise disjoint. Now, on the other hand, we can make a sort of analogous notion of tiling using the moment map to the hypersimplex. Okay, so again, we'll use the cell decomposition of the positive Grassmannian, and now we have this moment map, which maps surjectively onto the hypersimplex. And now a mu-induced tiling of the hypersimplex will be, similarly, a collection of closures of images of n minus 1 dimensional cells, because the hypersimplex has dimension n minus 1, such that the moment map is injective on each cell, the union of these pieces is the hypersimplex, and the interiors are pairwise disjoint. Okay, and just to be clear, when I'm looking in the hypersimplex case and I'm looking at closures of images of cells, these things are just polytopes. They are matroid polytopes. Actually, they're positroid polytopes. Okay, so up here we're cutting the amplituhedron into closures of images of cells, and down here we're cutting the hypersimplex into certain polytopes. Okay. And then what we conjectured with Lukowski and Parisi, and proved with Parisi and Sherman-Bennett, is that the tilings of the amplituhedron are in bijection with the tilings of the hypersimplex. Okay, and I'll just show what this looks like in an example. But the first question, of course, is how could we possibly relate tilings of some subset of the Grassmannian to tilings of a polytope? Okay, so let's just take the tiny example where m is 2, k is 1, and n is 4. In this case, when k is 1 and n is 4, our amplituhedron, so the k equals 1 example, and m equals 2, our amplituhedron was just a polygon. And so for n is 4, we just get a quadrilateral. And then on the other hand, our hypersimplex, in this k is 1, n is 4 example, is just an octahedron. Okay, so there are two tilings of the amplituhedron, and they will be exactly the two triangulations of a quadrilateral. And and I've drawn here how the cells map onto these tiles. So for example, this represents a positroid cell. Its decorated permutation is like this. And if you kind of go through how I described cells in terms of matchings of graphs, you'll see that this maps exactly onto this triangle. Okay, and then similarly, like this cell here maps exactly onto this triangle. Okay. Now there's also two tilings of the hypersimplex, and they are shown here. And you're either cutting the hypersimplex horizontally or vertically. The question is, how can you find a bijection between these two tilings? And yeah, and so the question is, and I've actually drawn them so that they correspond. So the question is, how can we relate this to this, this to this, this to this, and this to this? Okay, and so this is our duality, and it's actually a very simple map on the level of cells. So I told you that cells can be labeled by some permutations, and the bijection on the label of permutations is really simple. It takes a permutation that looks like this in list notation, and it maps it to this permutation. And this gives a bijection from the tilings of the hypersimplex to the tilings of the amplituhedron. Okay. In the k equals 1 case, this gives a nice corollary, which is that the number of fine subdivisions of the hypersimplex into positroid polytopes is exactly the Catalan number. Okay. And then I'll just mention that we were not sort of expecting any kind of connection between the hypersimplex and the amplituhedron. We had just been studying the amplituhedron when m equals 2, and what we noticed was that when we started counting the subdivisions of the m equals 2 amplituhedron, we were recovering numbers that, that were familiar to me because they agreed with the F vector of something called the positive tropical Grassmannian. And then we showed that those numbers enumerate subdivisions of the hypersimplex, and then made a bijection on both sides. So it was sort of, yeah, so there was no expectation that the amplituhedron should be related to the hypersimplex, but it sort of popped out from numerology. Okay, so just to summarize, the amplituhedron includes as special cases the positive Grassmannian, cyclic polytopes, and nice hyperplane arrangements. It's closely connected to the hypersimplex, and it's useful to study the amplituhedron from the point of view of matroids and tilings. And I think I promised in my abstract something about cluster algebras, but I don't think I have time. And there's lots of open problems, so I'll stop there. And this is a survey article that I wrote about this topic. So thanks a lot.
Does it say something about the recurrence that you mentioned?
The BCFW recurrence? So the BCFW recurrence has to do with the m equals 4 case. And then what we studied is what I was talking about with the tilings is the m equals 2 case. So it doesn't say anything about that. Yeah. Yeah, although interesting, Catalan still popped up.
Okay.
And this decomposition of the hypersimplex to positroids, is it projective?
No. That's just hypersimplex in affine space, and yeah, it's really just.
It means so they exist functions for which they would be.
Oh, are they regular? Is that what you're asking? You're talking about like regular subdivisions?
So I just yeah. So are they regular?
Oh, that's a good question. So the bijection that we wrote down is a okay. So yeah, in fact, I should clarify a little bit that the subdivisions of the amplituhedron coming from the positive tropical Grassmannian are the regular ones, and you use the element of the positive tropical Grassmannian as your height function. But what we wrote, this theorem at the bottom is a bijection for any subdivisions, regardless of whether they're regular or not. So this theorem, this bijection, gives a bijection between decompositions of the hypersimplex and decompositions of the m equals 2 amplituhedron, regardless of whether your decomposition on the hypersimplex side was regular or not.
So you have examples of non-regular.
Yes. Yeah, but what we don't know is how to make a definition, a good definition of regular subdivision of the amplituhedra, because I don't know how to talk about height functions and lower convex hulls or anything like that on the amplituhedron side.
So therefore it could be non-regular subdivision of hypersimplex, which correspond to.
Right. So that's how we define regular subdivision for the amplituhedron, but it's not. But it's only through this bijection. Yeah.
Yes.
Is there a way, if we take all of them all together, to put an algebraic structure on them?
Oh, sorry. All of which? All amplituhedron?
N, K, and M.
Yes. So let's see. So for sure, if we let, I think, K vary. So I forget if it's nice to look at K, N, and M all varying at once, but certainly it's nice to look at the set where N and M are fixed and K varies. Yeah. So some things in that direction have been looked at, but I don't remember exactly.
You see what I have in mind? I mean, if you take all together some families of polytopes, you can put operatic structure on them, like the isochahedra, for instance, the form of operad, okay? So that would be a tentative kind of algebraic structure to look on these guys. Interpret maybe the N and the M as some number of inputs and outputs of some operations.
Oh, I see. Yeah, I don't think it's been looked at precisely from that point of view. Yeah, but that's a good point.
So when we consider Grassmannians, we only consider them over the complex field, right? But if I were to change the base field, how would it? The theory.
Right. So in fact, when we define amplituhedron, we're even requiring more than complex, because it's defined using the positive Grassmannian, which is a subset of the real Grassmannian. And that positivity is required for this map z tilde to be well defined. But you could maybe relax that and just look at z as a rational map or something.
You mentioned twistor coordinates. It does mean that there is something hyperkerr behind.
Oh, not that I'm aware of. The twistor comes from twistor string theory. Oh, I don't know if that answers your question. Yes or no? Yeah.
I have a very naive question. So you show a correspondence between the different tilings. Yes, that's right. So do you have if you go back to your picture, the one where you were representing the different tilings, how you move from one to the other, there are operations of boundaries. And yes. So do you have in mind something global or?
Yeah, that's a good question. So you're asking, is there a geometric map that takes like this triangle to the top half of the hypersimplex? Is that what you're asking?
And how it's connected to the borders? You know, when you move from one tiling to the other, because clearly there is an operation. The way it's another
right.
one. And I was wondering, yes, whether you have the hope of a global correspondence.
Oh, right. So we looked a bit at that, and it extends, I think, to codimension 1, and it fails, or at least there's some nice properties on codimension 1. Actually, if we look here, then the codimension 1 faces are actually not in bijection. But some nice things are preserved to codimension 1, but then they fail lower down. And you know what is particularly confusing is that this map, if we're going from from this side of the picture to this side of the picture, is that this has dimension n-1, this has dimension 2k, and depending on what your k and n are, 2k might be bigger or smaller than n-1. And so it's sort of confusing to try to extend the map in, yeah.
Okay, thanks.
Yeah.
Naive questions. So then you just show picture about this cyclic polytope.
Oh, you mean the hyperplane arrangement?
Yeah, and then it's just like, but then it just come to me that hypersimplex could be also realized. So we have just this is matrix Z. So to look at these coordinates, then consider Zanatop. Some of these vectors, then you take Minkowski polytope, and if you consider section of the height k, then it would be exactly isomorphic to the hypersimplex.
Oh, okay. Maybe you can tell me that after the talk.
Yeah, exactly, because we have coffee break. Thanks again.
Okay, thank you.